guide us in our next chapter. Right, so let's move on. Now, before we go on to the potential energy, let's look at the metals again. Now, if we can stretch a metal to increase its length, let me say it is ductile. If we can change its shape to any form, we say it is malleable. Okay. Now, if the least force applied to the material causes it to break, then we say that material is brittle. Okay. So these are the words that we describe. Brittle is mean breaks. Okay, breaks is malleable and manipulate it. Okay, change it to shape. And ductile, you can draw it. Okay, draw it into wire form. But this is what I wanted. The last one I want us to have. Then just brief again, so that we get a concept for them. Because I want to have a very good discussion as we move on to the next topic, because that is going to capture about three. We're going to look at electric forces, we'll look at gravitational forces, then we'll look at magnetic forces. All these three, we'll look at them in the same picture so that you appreciate the similarities between them, among them, and then also appreciate why there will be some modifications in terms of formula or formulas. Okay, so here the principle is when you see the word strength, what does it mean? When you see the word potential, what does it mean? When you see the word density, okay, what does it mean? Okay, all right, and then just lines. So these lines will be lines of forces, lines of gravitational, lines of magnetism. And density, we are also usually looking at it with respect to area, or most often with respect to volume, but it can also be with respect to area. Now, when we talk about strength, we are looking at the measure per mass or measure per charge, depending on if you are being a charge. That's strength. When you talk about potential, you are looking at what measure per distance. Distance, okay? Measure per distance, okay? Measure per distance. Okay, force, we have said that force, the inverse square law applies. Force is proportional to the product of the masses and their distances apart, or if it is charge, Q times small p, we'll have that. Now, work done is equal to what? Your force in action, the force that is in the system, times the direction the system moves, times the distance the system moves. That distance is in the direction of the force, okay? Right, and that is work done. So when we have this, we have about how many? Let's say 1, 2, 3, 4, 5, 6. If you have these 6 concepts, well, graphs, okay, then the next chapter will be an easy thing for us. Okay, so get it well. The lines, okay, the flags, okay, that kind of flags is charge. Let's say this is a positive charge, okay. This magnet has lines of North Pole, South Pole, okay, right here. So again, the gravitational force is usually an attraction one. It's an attraction one, okay. The gravitational force is an attraction one. The electrical force can be positive or negative, right? So these principles, if you get them, then we can get somewhere with the next chapter that we're looking at. We want to get an understanding for electric, gravitational force, and then magnetism. So if you look at the pattern, you see that they follow. Once you're able to grasp that pattern, it becomes very easy to get the formulas and then be able to manipulate equations and work through. Okay, and this is it's a style that I've taught you. The point is, if we go that way, you wouldn't need to memorize the formulas, because the concept will be running through the same pattern as you move to electric, gravitational, and then magnetism, right? Now let's look at Kepler's laws. The Kepler's law. Okay, so if this is the sun, so we have the earth here, we have other heavenly bodies, let's say another one here, we have the moon, so there's the sun, this is the earth, this is the moon, is going around the sun like that, and the sun is also revolving around the earth. This is also another planet revolving around the earth. Okay, you can look at it this way, right? So in this case, what Kepler noticed, Kepler was working with his boss, but the boss was more secretive. He was keeping values to himself until he passed on. Okay, so when he passed on, Kepler had access to the data that they had gathered. Okay, so he used that data to sort of arrive at a certain conclusion. So let's look at the conclusion. So the conclusion was that for all the heavy bodies, interactions with the sun, okay, the distance, they all describe the first point is they all describe a path. The path that is described is what? Ellipse. Okay. So it's like an egg, ellipse. Okay. And then the second point is the distance. This distance. It is r. The distance that they sweep is always equal. That distance is always equal by the time it gets there. So the time and distance, okay, were the same. So let's say if it is 9:30, I'll be here. That distance, anytime 9:30, the distance is the same. Okay, so I'm just giving you basic understanding of this concept, so I don't need to remember. So that's it will sweep. So it means it sweeps equal or same distance at equal times. Okay, so here if it is 10:30, go so the same distance by the time it comes at equal times, it gets 10:30 again, it's the same distance. So it sweeps the same distance or it sweeps the same distance at equal times as it revolves. So this revolution, it is going around something, revolution. Turning around your body is rotation. Okay, so here as the earth is going around the sun or revolving around the sun, it is also turning on its own, on its body. That is rotation. And the same thing happening. The moon is turning on its body and is also going around the earth. And of course, the two are also going around the sun. Now, the moon is closer to the earth because of an attraction. Okay, some say maybe it's maybe a byproduct of the Big Bang theory, where part of, or let's say the continuous separation of the earth gave rise to this one, so that it's still close and it's holding on to it. That is, these are, theories that have been propounded. Right, so that's the second part. So time sweeps the same or equal distances at equal times. Okay, that is it. And the third part, he realized that the square of the period, the time taken to make one revolution, was proportional to the cube of the distances between the cube of the distance between the sun and then the heavenly body. Now we are going to look at how we arrived at this, and then how by mathematics we can arrive at this deduction. Now we know that if this is the earth and it is revolving around the sun, it's going around the sun, there is a force directed towards the center. Assuming this is a circle, it's a force directed towards the center we call the centripetal force. Okay, this centripetal force, we said is given by this. This is the centripetal force. Okay, because we said it's mass times force is mass times acceleration, and we know acceleration is equal to mv squared over r from our circular motion calculation. So centripetal force becomes that. Okay, in this case we have taken care of the circular part. The r is accounting for the circular part. So that is the centripetal force. Now this is the centripetal force. We can replace this one, can write this in terms of angular velocity. So that our angular, this the force, which is the centripetal force, first when it's going like that, we have the tangential force. You have the force that is directed towards this way, and then you have this one, which is always directed towards the center and is proximate to this one, and that is the centripetal force. This centripetal force can also be written as this, we know V is equal to R omega, just as we say a linear acceleration is equal to R angular acceleration. So V, it's angular acceleration, it's angular. Right. So we can put, in place of V here, we can put this here. Okay? Now let's see what happens. If we put that there, then the equation will become Fc, or F is equal to, as the force, is equal to m, okay, the mass of the body, F, that is revolving, R squared omega squared over R. Now this will come out as what? M, R will cancel 1, so R omega squared. This is the formula that we have come out with, right? Okay, so having arrived at this formula, let's see how we can relate this to the force. This force must also be equal to the force of attraction between the two bodies. We know the force of attraction between two bodies is given by G, the capital M, small m, over your R squared. Okay, now the sun is a constant in all these relations that we are looking at. So we can say this is more or less a constant. And then we will have so from there, and then we're going to have from here, then we're going to have this. This is a constant because J is constant, mass of the sun is also constant, so it becomes K M over R squared is equal to M R omega squared. This is where I want us to look at that. Okay, now let's get a relationship for T and R. Let's see how it goes. Now T is given by 2 pi over omega. You remember that in our previous discussion where we talked about the rotational movement, okay, where we talk about omega, and then where we talk about circular motion, we talk about this kind of formula. It's more for circular motion or simple harmonic motion. We talk about that, right? So here, in place of this, we can substitute this so that we have T in the equation. So let's see how T will come into the equation. Now this mathematics we are doing was done by Newton. So Newton was evaluating the values that, so this calculation was done by Kepler. And then Newton will evaluate the relationship. This house is inverse square root of Kepler's data, okay, or Kepler's calculation. So from here, we're going to do substitution. So here, we are going to substitute here. This implies that omega is equal to T, is equal to 2 pi over T. So we're going to substitute that one here. Therefore, we have Km over R squared is equal to M R. We're going to put this one there, and it's squared. So we're going to have 2 pi over T squared. This M will cancel this M, so we have K over R. K over R is equal to R squared is equal to. So this R will also cancel 1. As we have the, let's do the expansion first and see. R, let's expand, this is going to give us 4 pi squared, all this over T squared. Okay? What are we seeing? Let's arrange the R so that this R will come. So that we can write, let's turn it, or let's say, let this go here, then this comes here. So we have K, T squared is equal to R squared, R, 4 pi squared. So this is going to give us T squared is equal to R, and is going to R cubed, 4 pi squared. Okay, see, right. Now let's arrange properly and see. We have T squared is equal to 4 pi squared K R cubed. Now what do you notice from here, this equation? What do you notice? Now this is a constant, this is a constant, this is a constant. So this whole thing is a constant. Therefore, you can see that T squared is proportional to R cubed. This is it. This is what Kepler came out with. Right, so that is what we have now. Now, so having arrived at this point, Newton came into the picture in the 1660s, okay? Right, and then he wanted to find out the, in terms of force of attraction, the relation between the two bodies with respect to the distance apart, okay? All these, you should remember, were being done by using data that were gathered in the previous years. Right. So Newton was also building up upon Kepler's conclusion that the period squared is proportional to the distance apart for the two bodies involved. All right. Okay. So let's look at what Newton also did. So from here, he came on to the point that because this was related to this, and it proved this proved this relation based on data that was gathered by Kepler. Then he came up with what we call the inverse square law. So that from this we can say that the force of attraction between two bodies, would be proportional to the product of the two bodies, if it is masses that we are talking about, or the charges we are talking about. This same force is also inversely proportional to the distance squared. Okay, so putting the two together, we have F is equal to, anytime you remove the proportionality sign, you bring the constant. There's a constant that should multiply that. This is going to be this. Putting the two equations together, R O K, and this is where I said we can relate the three forces: electrical force, gravitational force, magnetic forces. So we can look at it. Now we'll have an equivalent equation for magnetic force when it comes to, for magnetic force, it's one body, not between two bodies, it's one body which is radiating its magnetic field, okay? But of course, we can also look at two bodies, two magnets having effect on each other, okay? And that will also give us an expression which will also have in it part of these kind of expressions, okay? All right, so this brings us to the inverse square law, and then we have proved Kepler's third law, which relates the period, time taken to make one revolution, to the distance being swept by the body as it revolves around the sun. Right. Now, before we go to that, let's assume that we have a body like that, a couple. This is a couple. That means the forces are acting in the same direction. Okay. Let's assume these are two bodies. Okay. Now, the two bodies will have force of attraction between them. Let's say K, M, R squared. Okay. Let's say the distance is D. Okay. Now let's assume this is a twist. It's going to cause a twist, a turn, and then can look at that twist like that. Okay. That is multiplied by, let's say, constant C. So that torque, okay, or torsion, okay. Of course, this is giving us torque, okay. Torque 10, or torque for a couple is that it's multiplied by distance between the two, not half of the distance, because it's they are parallel forces, okay. So in that case, the torque can be equal to this. This is a property of the torsion, okay, and this is a constant. From this, we can do calculations, okay. So some of the experiment that can be used to arrive at the finding constants and so on, right. All right, so let's look at this table, and this was the table I was talking about, that we should have a very firm understanding of what line of flux is, line of forces or flux. The density, when we say density, what we are looking at, if we look at strength, what we are looking at, if we look at potential, what we are looking at, look at the force, we are looking at what we are looking at, and when we look at work done or energy. Let's go here, energy. Okay. This energy can be kinetic energy, can be potential energy, or the two together, and so on. Right. So, if you look at it from this picture, you see that this is under gravitational properties. Then we have electric and electricity, electric field, gravitational field, electric field, magnetic field. Now, so the lines of forces, these are the lines of forces, okay? For gravitational field, the lines of forces is attraction. Okay. For electric field, the electric field. So gravitational field is magnetic field. So for electric field, we have the lines of forces. Okay, these are the lines of forces. These are positive side. So as if you are bringing a positive, it will be repelled. Okay, it can be between this and a positive, between this and a negative. Right. So here you have positive and negative signs. Okay. Now the magnetic field, it can be magnet itself attracting another one, or magnet itself with its field. Of course, we have also you come to realize that any time electrons flow, when electrons are moving, we call that current. Okay, when they are moving, opposite that direction is a current. Okay, that's a convention, and that is how we have agreed to accept it. That when electrons are moving this way, we accept that electrons are going this way. It was an error that was made in the ancient times. Okay, so we have carried it forward. Okay, now so the point is, anytime electrons are moving, okay, if you remember the chemistry, electrons are moving, they are spinning as well, and the spin gives them some kind of magnetic field around them. Okay, so when a body is moving like that, if this stamp is in the direction of the current, so let's say current is this way, because it's current to opposite the electrons. Then the field, electric field around it, okay, and the magnetic field around it will go in that order. Okay. Right, so that will be the magnetic field. So there's a relationship between electrons flowing and magnetic field. So that's flux, the magnetic field lines. Okay. Then come to the density. So it is either these lines that we have over an area. Over an area. That would be that. Of course, density gives you a picture of something over volume, but it can also be related to area. That's what it gets. So when it comes to magnetic field, what we call the magnetic flux density. So the lines are the flux. The flux density will be flux over area. That's the magnetic flux density, right? And it's denoted by B. Okay. Now, when it comes to strength, looking at strength, we usually will be comparing with the body. So here is the body that we're talking about. The body can be mass or can be charge. So the force per mass or force per charge, okay, that will give you the strength, the strength, okay, and of course that will be proportionate to the flux density for magnetic field, proportionate to the flux density, the strength there. Right, now if you talk about potential, like I said, these are ways to guide you. Potential is with respect to distance, okay, with respect to distance. To distance, okay. So the work done is, and it's also with respect to work done. So the work done per distance, over a distance, okay, at a distance, over a distance, okay, is potential, the potential, okay. So it can be gravitational potential, electric potential. Of course, we are looking at in terms of sense, we look at it that way for magnetic, okay, but that one is usually related to P. Okay, so here the work done over R. So you see that I've put here, work done is force times distance. This is the force that we are defined. Force is defined by the inverse square law. Okay, this force times R gives you this. So if potential is work done over R, then it's this work done divided by M for this one. M cancels, and then you have what? The final answer is what? K capital M over R as the potential. Okay? So this will also become K capital K over R as a potential, electric field potential, right? So now when it comes to force, this is from the inverse square law proposed by Newton, okay? So the force is directly proportional to the product of the masses or product of the charges involved, and then it's inversely proportional to the square of their distance apart. So distance apart. So that there's a similarity. You see that's what is flow. And then once we remove the proportionality sign and bring in, we have a constant. The constant in the field of gravitational force is a capital G, which is the gravitational constant. Here in the field of electric force is K, and K is, that constant is related to more or less like a sphere around it. Okay, so the 4 pi is giving a picture like a sphere. Okay, and then the space, is it vacuum? Okay, the permittivity of the space, okay, is given by that. So that is the constant replacing this. Okay, so then if you come to magnetic field, you see that force is proportional to, is defined by this method, by this expression. It's actually force, the force is proportional to the magnetic flux density. It's also proportional to the current flowing. It's also proportional to the length of the wire in which the current is flowing. And it's also directly proportional to the angle between the point from the point in the field to the body, the wire. That's one. That's what we've done here. So this is the wire. This is a point. is the distance. That angle, this angle, sine of this angle, the force is always proportional to the sine of this angle. Okay, that is from an observation of or from data gathered. Okay, so in that case, if this is proportional to this, it's also realized that B is proportional to this. This is from the Savio view. Sorry, Savart view law. Okay, Savart view law. Okay, or as I say, SB law. Okay, the law is there. Okay, and then that is, if you look at it carefully, you see that there's some correlation between this, the force that we are looking at here. Because this is in this, it's in the same as saying that F is proportional to this. Okay, you see the square is there, the distance, but square. Okay, now here this is representing the current flowing, which is the electron, like the charge. Okay, the charge. Okay, the charge. Okay, that's flowing. Okay, right. So that is what we have here. So the two charges, and then of course the quantity of charge is the current is flowing through this amount. And then this one, we are looking at it in terms of angle in space, how it is distributed. I mean, the forces are distributed. Of course, that is the. So you see that at least there is some correlation that will make you remember that is it. Right. So at that point, right. So that this will. So Savart view or view Savart law. Okay, this is referring to this one. Right. So you see that is the intense of forces, that is where it is. Okay, so when you come to work done, say work done is the force that is involved, and then the distance in the direction of that force is giving you the work done, and that is the energy equivalent. Okay, and of course this is the expression for force, so times the distance. Let's say the distance is r. This is what we have. Okay, the two bodies involved come closer by a distance, certain distance r. If you move one from that distance to the surface of the bigger one, okay, this will be the work done. Okay, and that will give you the energy, or the energy in that system between the two. So that is the measure. Of course, this becomes G, capital G. K is G here, K is G here, right? And then, like you said, K, when it comes to the electric field, it's the same thing, work done. So the same thing, the force will be this one times R, and it will reduce to this, okay? Right. So it is the same as this times R. So this cancels one, and this goes one. And then that was K, Q, small q, R. Of course, K is the same as 1 over 4 pi, epsilon naught, okay? Then you have your Q, small q, and you have your R there, and that is the work done. Okay, when you come to the magnetic field, you should know the force that is involved, and then the distance that has, moved in the direction of the force, Then that will be the work done. Okay. The other thing that you should note is we will be making the potential. When you are talking about potential, the references, the references can be between the bodies, okay, which usually will give you a positive number, or we can look at the references from infinity. So if you go from infinity to a point, then it becomes negative. Okay, you get a negative answer. Okay, from infinity to a point. Okay, that means below 18. So moving a body from infinity to that point, the change will be what? So initial is final minus initial. Okay, but the force at that point should know the value. So if you say the change, you are looking at the what? The final minus initial. Okay, so depending on the charge that you are dealing with, okay, you may get a positive or a negative depending on the reference point that you are using. So depending on how it is moved, whether it's moved from infinity to the point or from that point to infinity. Right, but that should be noted, you should keep that in mind, so that when you are doing the subtractions, you know, for instance, if we are looking at gravitational force, if you are looking at the gravitational force at the point, we look at it like moving the mass from infinity to the relationship between infinity and that the location of the mass. Okay, right. So because the infinity is a reference, what you are subtracting from, it makes the whole picture, it makes the whole expression have a negative sign. That is with reference to infinity. However, it's reference to the Earth's surface, two bodies on the Earth's surface, we are looking at the Earth as a reference point, then you're having a positive figure for potential energy, especially. Right, so that is that. So this is a brief summary of what we have discussed. So from this, we will look at the other pictures. Now we'll take gravitational force and then finish it and move on. So this should be at the back of our mind as we progress through the topics. Now let's take time to go through briefly the reference points. Okay, so let me just create this small space so that let's say if we are dealing with gravitational field, there's the Earth, there's the body infinity. Okay, the body at infinity. Now the potential energy here, the potential here, let's say V, and the potential at the surface of the Earth. If you want to find the potential at the surface of the Earth, we assume like moving a mass, a unit mass from this point to this point, the energy change, okay, that will be the potential. Now, in terms of potential, which is energy, in terms of potential, the further this one is, the greater energy will be involved if it is moved down. So, it means if you are moving from, let's assume from infinity, the potential there is 0, and here potential is very high here. Sorry, the potential here is at a certain value. Certain value. Now, because from here to here, the work done is going to be very high. So from your initial, final minus initial, okay? Your initial is greater than your final. Because we are saying the potential at the infinity is greater. With reference to the surface of the Earth, then the potential at the surface of the Earth is going to be negative. We're going to have negative view for the potential of the surface here, because this is higher than this, and then we are saying this is 0. We are saying the farthest is 0. If the farthest is 0, then anything below it is going to be negative. But when it comes to charges, it may not work so. Okay, the charge will look at the strength. Okay, we are looking at the charge, the strength as you move. Okay, the strength as you move, it gets weaker. But we break down, the further you go, more work is done. With strength or the charge, as you move further, the charges may reduce, okay? So that may not work as we have said for. So defining the potential of this will always be negative. So potential, for instance, here, this will become a negative G N over R for this expression where we have potential. Well done by that. If you are looking at the potential at the surface of the Earth, it will have a negative value with reference to infinity. Where we assume conventional that let infinity be 0, then all that will be negative. If we are using the Earth surface as potential, then all potential will then be considered as positive. Okay, right. Or two bodies close together, then the potential that we are looking at, because at the Earth as reference, then it will not be as we have made reference to the infinity. Okay. So that's the point I want to make. So at this point, it's very simple. Look at the similarities. This, and that. You have similar, and this will help you to even remember the formulas. If you forget them, you can easily deduce the formulas. Right.